morning everyone. Today, our group will demonstrate how calculus provide practical solution to real-world engineering challenges. Before we proceed, we would like to introduce ourselves. My name is Ahmad Nafis.
My name is Katiresh.
My name is Imarifai.
We have chosen to focus on optimizing the volume of a water tank, especially applying the concept of maximum and minimum points from our syllabus.
Imagine we are tasked with building a household water tank designed to hold exactly 10,000 cubic centimeters or 10 liters of water. As engineers, our priority isn't just functionality, it is also cost efficiency and sustainability. By finding the dimensions that require the minimum surface area, we can significantly reduce the amount of metal or plastic needed for production.
To achieve this, we will model the tank as a cylinder and use differentiation to find the sweet spot where volume is maximized and material waste is minimized. My teammate will now walk you through the mathematical setup and the modern tools we use to visualize this function.
Imagine we are tasked with building a household water tank designed to hold exactly 10,000 cubic centimeters or 10 liters of water. As engineers, our priority isn't just functionality, it is also cost efficiency and sustainability. By finding the dimensions that require the minimum surface area, we can significantly reduce the amount of metal or plastic needed for production.
To achieve this, we will model the tank as a cylinder and use differentiation to find the sweet spot where volume is maximized and material waste is minimized. My teammate will now walk you through the mathematical setup and the modern tools we use to visualize this function.
We are focusing on a maximum and a minimum point to solve this. Imagine we need to build a household water tank that holds exactly 10,000 cm3 or 10 liters. As engineers, our goal is to use the minimum amount of metal sheet possible. This is not only save material costs, but also promotes sustainable manufacturing. My teammate will now explain how we set out this problem using geometry and modern tools.
To solve this problem, we represent our water tank as a cylinder. We have two main geometric variables, the radius and the height. Our fixed constraint is the volume, V equal to 10,000 cm cube. The formula for volume is V equal to pi r square, H equal to 10,000. Our objective is to minimize the surface area A, which represent the material cost. The formula for closed cylinder is A equal to 2 pi r square plus 2 pi r h. To differentiate this, we need the area in terms of only one variable r. By rearranging our volume formula, we find that h equal to 10,000 over pi r square. Substituting this back into our area equation, the pi and 1r cancel out, giving us our final function A equal to 2 pi r square plus 20,000 over r.
Now we apply the rules of differentiation to find the stationary point. We find the first derivative of the area with respect to the radius dA over dr. Differentiating 2 pi r square gives us 4 pi r, and differentiating 20,000 over r gives us negative 20,000 over r square. So our derivative is dA over dr equals to 4 pi r minus 20,000 over r square. To find the minimum surface area, we set the derivative to 0. 4 pi r minus 20,000 over r square equals to 0. By multiplying both sides by r square, we get 4 pi r cube equals to 20,000. Solving for r, we find that r equals to square root 3 20,000 over 4 pi. Using a scientific calculator, This gives us an optimal radius of approximately 11.68 cm. Plugging this back into our height formula, we get a height of 23.33 cm. After applying the first and second derivative test, we successfully identified the stationary point. Our calculation show that the optimal radius is approximately 11.68 cm with the height of 23.36 cm.
Using the second derivative test, we confirm that this dimension result in an absolute minimum surface area, meaning we have used the least amount of material possible for the required volume. This project proved that the calculus is an essential tool in a modern engineering for creating efficient, cost-effective product.
Thank you. That's all from us.